G'day, mathletes. Welcome back to McGrathematics, the fastest growing maths YouTube channel in my entire neighborhood. Today on the channel, we're going to look at some volumes of rotation questions from the Extension 1 HSC course, looking at a bunch of HSC questions of rotating around the X and Y axis, hopefully to help you prepare for your upcoming trials and maybe even your HSC exams. Okay, so let's dive in. Let's just talk about how we find volumes of rotation first, and then we'll dive through a few examples to give you guys a better understanding. Okay, so just starting off, just a quick recap of how we find areas using integration. If you want to find the area under a curve between two values, all you've got to do is integrate that curve between the two values. The quick version of how this works is you're essentially just adding together a lot of little strips to form this solid area. Okay, so the Y values are strips, and then add all the strips together, and then you make a shape. That's the really quick version. If you want a more in-depth explanation than that, that's way above my pay grade, so sorry. Now, what happens if we take those strips, and instead of taking them as strips, we think about them as a radius of a circle. So we take that strip and think of it as a radius, we square it, and then we times it by pi, and now that strip turns into a pi r squared, so it turns into a circle. So now instead of adding together a bunch of little strips to make an area, we're adding together a bunch of circles that form a 3D solid in this case, okay? So instead of adding together y's, we're adding together pi y squareds, and that's why our formula looks something like this if we are rotating around the x-axis. If we were rotating around the y-axis, we would just swap the variables, and our two limits would be y values, and we'd be integrating with respect to y. Okay, so these formulas are on the reference sheet, but you just got to remember which one is the x and which one is the y. And the hint is just the thing on the x, okay? If it's got dx, it's the one for the x-axis rotations. If it's going around the y-axis, then the formula has the dy on it, okay? So this time we're taking circles going vertically, adding all the circles together, and then forming a solid, okay? You don't really need to know the theory behind it. Just knowing how to use the formula is going to get you through the majority of these questions. So we'll start off with some x-axis rotations, and then we'll look at a few y-axis rotations to give you an idea of the whole topic. So here's our first one. This one is from the 2019 HSC. It's from the 2019 HSC Advanced because before 2020, volumes of rotation were in the Advanced course, and now from 2020 onwards, they're Extension 1 content only. So that's why this one is a little tiny bit easier. So I've got the diagram showing the region bounded by the curve x minus x cubed. The x-axis between 0 and 1. We're going to take this area shaded in gray. We are going to rotate it around the x-axis and make a solid. We are going to find the exact volume of the solid formed. So exact means that we can't use our calculator. We've got to simplify our answer as much as we can because we want to have an expression for the answer rather than a decimal to get full marks. Okay, so straight away, we're going around the x-axis. So let's use our x-axis rotation formula. On the reference sheet, you just got to know what you're looking for. A and B are our two x values that we are rotating between, which in this case are 0 and 1. Now, y is equal to x minus x cubed, but we want to be integrating y squared with a pi at the front, because again, it's making a pi r squared, it's making a circle, adding them together to make a volume. Blah, 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 who cares? Okay, so first thing we're going to do is take our equation, which is y equals x minus x cubed, and we need to find y squared by squaring both sides like this. And now to integrate the right-hand side, we need to expand this. So we're going to do a little perfect square expansion, and that can sometimes be the hardest part of these questions if the algebra is a bit hectic. So we're going to do the first term squared is x squared. Then for the middle term, we're going to times the two terms together and double it. So we have 2 lots of x times negative x cubed. Then on the end, we are squaring the second term. So we are squaring negative x to the power of 3. So we have x squared at the front. In the middle, we make an x to the 4 with a negative 2. And then on the end, when you square a negative, it becomes positive. And x to the 3 to the power of 2 is x to the power of 2 times 3, which is x to the 6. Okay, so now we have gone from our y equals to our y squared equals. And this line right here is what we need to integrate between 0 and 1. Chuck a pi out the front and then try and simplify our answer as best as we can. So let's dive into that. Getting rid of that, and now integrating our expression we just expanded. And now we're just going to use our power rule here. So we're going to raise all these powers by 1 and then divide by the new powers as per your stock standard integration. So we're going to get x cubed on 3 minus 2x to the 5 on 5 and then x to the 7 over 7. Pi is still at the front. Don't forget about that. We're going to put him in right at the end. Our limits are 1 and 0, which are mercifully as nice as they could possibly be. When we sub 0 into all three of these terms, they're all just going to turn into nothing, which is very convenient. So when we sub in 1, we get 1 over 3 minus 2 over 5 plus 1 over 7. So that's us subbing in x equals 1. And when you sub in x equals 0, like I said, they all just turn into nothing. So it's just minus 0. Okay, we can simplify these fractions with a calculator or with a pen if you're an absolute legend. And then you should end up with the final answer simplified as 8 pi over 105. Now, because we are finding a volume, we're just going to leave our answer as u cubed, which is just shorthand for cubic units. So it's exactly 8 pi over 105 cubic units. Okay, so the structure of these questions is write down your formula, figure out what your y squared looks like, integrate, sub in your limits, and then you're done. Okay, they're typically always 3 marks, as we can see this one is. The more challenging ones can be 4 marks. So there'll be a couple of them today. Okay, on to our second x-axis revolution. This is the famous egg question. I love eggs. We have 2 curves, C1 and C2. C1 is a semicircle, which we can see on the left-hand side. Radius 2 centered at the origin, and we're just doing the left-hand side, hence the x limits. And the right-hand side is half of an ellipse, and the equation of the ellipse is given here, and we're just going between 0 and 3 to get the right-hand side of the ellipse to make this cool little egg ball thingy. We're going to rotate this shape, this region, around the x-axis to actually form an egg, and we're going to use the power of mathematics to find the exact volume of this egg, which is really fun. Okay, so for this question, because it's 4 marks, there's a bit more work to do. Because we have 2 different functions and two different areas, we need to do our volume in 2 different sections. We're going to take the semicircle and we're going to rotate it around the x-axis. Then we'll take the ellipse and rotate it around the x-axis to get 2 volumes, sum them together to get our final answer. Also worth noting here that by rotating the semicircle around the x-axis, you're making a hemisphere. And so if you already know that the volume of a hemisphere is 4 over 3 pi r cubed, you don't really need to do any calculus if you find that easier, which I think from memory is what we're going to do here. Okay, so here's our 2 curves. Left-hand side is the semicircle, right-hand side is the ellipse. Now for the semicircle, here's our formula for going around the x-axis, of course. And we're looking at the first equation. We're just going to rearrange this to make y squared. So subtracting the x squared over across the right-hand side, we get y squared equals 4 minus x squared. And so now this is what we are going to integrate because we want to integrate y squared. Okay, a and b are the 2 x values we're going between. So we're starting at minus 2 and we're finishing at 0. So we're going to be integrating from negative 2 to 0 of 4 minus x squared with a pi out the front. Okay, now integrating with our power rule. 4 turns into 4x. We get x to the 3 over 3. Our limits are 0 and minus 2 with a pi out the front. Now, when we chuck the 0 in, everything will just be equal to 0. So we're just going to really worry about the minus 2. So setting up our limit sub in now, we have the 0 out the front, which is just both of these turning into nothing. Then we're subtracting and then subbing in the second limit, which is minus 2. So I'm putting it in here with the 4 and putting it up here with the cubed. Okay, so 4 times minus 2 is minus 8. When we cube minus 2, we're going to get negative 8. And the negative out the front is going to make that actually a positive 8. So we'll get plus 8 over 3. And then we'll have a minus 8 out the front, which looks like this. And then apparently cutting to the chase, when you sub all that into the calculator, it simplifies to one simple fraction as 16 over 3. Don't forget your pi out the front. So the volume of the hemisphere is 16 pi over 3. Okay. Once again, if you'd found that area by doing the volume of a sphere and then halving it, so 4 over 3 pi r cubed divided by 2, you could get this answer and you would still obtain 4 marks because it is still valid. All right, so there's left-hand side. Let's make a note of that over here. Left-hand side is equal to 16 pi on 3 cubic units. Now for the right-hand side, we're spinning the ellipse half around the x-axis again to create the rest of the shape. So this one requires a little bit more rearranging. We're taking our equation given to us by the question and we're going to rearrange this to make y squared because that's, as always, is what we're going to be integrating. So we're just going to minus the x squared over 9 across the right hand side. So we have 1 minus x squared over 9. And now we'll just times both sides by 4 to get y squared by itself. So this will turn into a 4, and this will turn into a 4x squared over 9. So this right here is our y squared. This right here is what we need to integrate. Our two x values for the ellipse part are going from 0 to 3. So those are our limits, 0 to 3. Okay, integrate from 0 to 3, pi out the fronts, and now going through the motions again. 4 integrates to 4x, raise the power to x to the 3, put a 3 on the bottom, and that 9 turns into a 27. And now subbing in our limits again, 0 is going to make everything just turn into nothing, which is convenience. So we just got to worry about putting in the 3. And so we'll get some space, and we'll do 4 times 3 is 12, minus 4 times 3 cubed over 27. Then I'm just doing a minus 0, so I can show to my marker that I know that when I put 0 into this expression, I do get nothing. Okay, you shouldn't leave that blank. You should explain your working as much as possible to get full marks. Okay, and then this simplifies inside to become 8, would you believe? Because we're going to get, oh yeah, because 3 cubed is 27. And so the 27s cancel out, and you get 12 minus 4, which is 8. So the right-hand side of this volume, from 0 to 3, rotated around, gets us 8 pi. So to get our final answer for full marks, we're just going to have 8 pi and 16 pi on 3 being summed together for our total volume. Okay? Probably should have wrote units cubed after that, and probably should have combined them into one fraction, but hey, that's the correct answer. That's going to be getting me 4 marks if I was sitting this in year 2016 HSC. Once again, because this question is a little bit older, this is from an advanced paper, but this is one of the harder ones that was found in the advanced paper pre-2020. So 4 marks, pretty tough. Okay, sweet. That's enough egg chat. Let's move on to the third one, which is a little bit tougher because this one is actually from... I did combine them. Oh, I'm so good. Combine them into one fraction, give a units cubed, and that's an even better answer. I'm so proud of myself, and I'm ashamed I forgot that I was actually going to do that. All right, now on to the third one. This one's from an Extension 1 paper because it's post-2020 in the new age of maths. It's 3 marks, but it is pretty tough. We are looking at rotating k plus 1 sine kx, k is positive, between 0 and pi over 2k around the x-axis. Now, we don't know what the value of k is, but we want to figure it out, given that the question has told us that the volume of revolution around the x-axis between these two values has an answer of pi squared. We need to use that information to solve for k. So this one is really tough. I think it should have been 4 marks. I think 3 is a bit tough, but let's go through and see how we go. So we are rotating around the x-axis. We go straight to our x-axis rotation formula. We know it's this one. Don't be tricked by the y squared there. Just look for the dx, and you know you're working with the right one. Okay, so we have our equation up here. We have y equals bloody blah. We need to figure out what y squared is by squaring both sides. So when we square this, we're going to get k plus 1 squared. And when we square sine kx, we of course get sine squared kx. Okay, we've got to pi out the fronts. Our two limits are 0 and pi over 2k as the question specified. Okay, now we need to integrate. So the k plus 1 squared is a constant, so I can put that at the front of the integral to make my life a bit easier if I want. And now to integrate sine squared or cos squared in the Extension 1 course, there is a formula you use off the reference sheet, which tells you that sine squared... oh, I'm so sorry, long day. That sine squared of something x is equal to half of 1 minus cos of 2 times the angle. Okay, so all I've done there is move the k plus 1 squared out the front because it's a constant, like I said, and just change sine squared to be equal to a half of 1 minus cos 2kx. That's straight off the reference sheet, and hopefully something you've already been shown in class, or maybe on this channel if that's where you're learning. Okay, now we're going to do some integration. I'm also going to move the half out the front just to make life a little bit easier because it is a constant. So make some room. Put the half out the front to make this over 2, and now integrating the inside. 1 is going to integrate to x, and our cos integrates to sine. Of course, when you differentiate or integrate cos or sine, the angle has always got to remain the same. Except when you're integrating, you need to divide by the derivative of the angle. Because the angle is 2kx, the derivative would be 2k. So that's why I've put a 2k on the bottom there. Okay, so cos turns into sine, angle stays the same, divide by the derivative of the angle. Those are your 3 steps. Okay, now we're going to sub in some numbers. So when we sub in 0, mercifully, we get nothing because we just get nothing here and we get sine of nothing, which is just nothing, okay? So we really just need to worry about the pi over 2k. So if we sub that in, we get a pi over 2k here, and then in the sine, we get 2k times pi over 2k. So that's us subbing the pi over 2k into the angle. Now, because these 2k's are the same on top and bottom, they're going to vanish away and leave us with sine pi. And sine pi, which is sine 180, is equal to nothing. So this whole term here in the middle just turns into nothing, thankfully. And so the whole thing inside this bracket really just turns into pi over 2k. So we'll do that up here. Okay, so again, sine pi is nothing, so this turns into 0. We get pi over 2k. And then don't forget the pi, k plus 1 squared over 2 out the front. That's going to multiply our answer. And so the pi's are going to go together and make a pi squared. And on the bottom, we're going to get 2 times 2k, which is 4k squared. That right there is our expression for the volume of this solid of revolution. Now to solve for k, the question told us that this volume is going to be equal to, I think it was pi squared from memory, wasn't it? Let's have a look. Pi squared, yeah, okay, cool. So here is our equation to solve. Find where the volume is equal to pi squared and solve for k. All right, so because there's a pi squared on both sides, we can just divide by pi squared and get k plus 1 squared over 4k is equal to 1. Now we can multiply the 4k across to the right. While we're doing that, we may as well expand the top as our perfect square. K squared plus 2k plus 1 equals 4k. Now to solve for k, we can just take 4k off both sides because it's a quadratic. Jeez, I need some water or something, hey. Okay, taking 4k off both sides looks like this. Now we can refactorize because the left-hand side is still a perfect square because this is k minus 1 all squared because, you know, that's the two things that add to give minus 2 and multiply to give plus 1. So we get k minus 1 squared factorized, and now it's super easy. We can see that, well, if this is equal to 0, it means that k minus 1 is equal to 0, which means that k is equal to 1, okay? And the whole solution to this convoluted problem was the most simple possible answer, that k is just equal to 1. Okay, so 2 marks there if you manage to get this expression in red for your volume, and then 3 marks if we solve this equal to pi squared and get k equal to 1. Okay, that is the x-axis rotation questions done. Now we'll do a few y-axis rotation questions done for a bit of variety, and then you've covered this whole topic. Okay, first y-axis rotation question. This one comes to us from the 2015 Advanced HSC, back in the days of advanced content. And we are making a bowl. Why would you join a pottery class when you can just do extension 1 maths, hey? We're going to rotate 8 log base e of x minus 1 around the y-axis between 0 and 6 to make a cute little pottery bowl. We're going to find the volume of it. This time we don't have to give an exact answer. We can leave it correct to 1 decimal place using a calculator. Okay, so as soon as we see y-axis rotation, we either write down the formula that we know or we go to the reference sheet to jog our memory. And we know it's the y-axis formula because it's got the dy on the end. So a and b are going to be 2 y values. So we're rotating between 0 and 6. So those are our a and b. We have an equation given to us y equals. We need to find x squared. Okay, so this is the hard part of the question. We need to rearrange this equation to make x the subject, and then we need to square it. So the setup is really the harder part of these questions for the y-axis usually. Let's have a look. So we'll start with y equals 8 log base e of x minus 1. Now we'll divide both sides by 8 to get that over there. And now we want to get rid of this log from both sides. So we're going to raise both sides to the power of e. When you raise the left-hand side to the power of e, it gets rid of the log base e because they are inverse operations. And the right-hand side turns into e to the y over 8. Now we'll just plus the 1 across the right-hand side and we have x. So first step's done, we have x. Now we need to get x squared so we have something to integrate. So we're going to square both sides, okay? We're going to expand this out using a perfect square expansion. We're just going to do the quick version this time. So when we square e to the y over 8, we're going to get e squared y over 8. We're going to times these two together and double it to get 2e to the y over 8. And then the last term is 1 squared. Okay, so this here is our term that we are now going to integrate. We can make 2y over 8 equal to y over 4 to make it a little bit nicer. But here we go, diving into some calculus. So here is what we need to integrate between 0 and 6. So let's do that, shall we? Yes, we will. Okay, cool. So integrating exponentials, with exponentials, we always keep them the same, except we divide by the derivative of the power. So the derivative of this power is going to be a quarter, and the derivative of this power is going to be an eighth. So it's going to get very fractiony. Don't forget the pi at the front, or your answer will be completely wrong, and then you'll fail, and then it's goodbye Harvard, hello, living under the bridge. Okay, so we have e to the y over 4 staying the same, dividing by a quarter. 2e to the y over 8 staying the same and dividing by an eighth, and then the 1 integrates to a y. Okay, now to tie this up a bit, when you divide by 1 over 4, this 4 is actually going to go up the top and times with this. So it's really going to be a 4 up top here, and we're going to have an 8 up top here, making this 2 into a 16. So it's good to know that when you have a fraction under a fraction, the very lowest denominator is actually going to flip up the top. Okay, so we have a 4 here, we have a 16 here, and we have a y here. We're going to chuck in y equals 6, and we're going to chuck in y equals 0. Y equals 0 is not going to make everything equal to 0 because e to the 0 is equal to 1. So we are going to get some values. We'll do that over here. Yep, just here. Okay, cool. So here is us chucking in 6 in the place of y, and here is us chucking 0 in the place of y. Now, because we're getting a 1 decimal place answer, you can just chuck all this into your calculator at whatever point you want. Going straight from here to the answer to 1 decimal place will get you full marks. Can't remember how much I did. I did a little bit more, simplified, and then chuck it into the calculator, and you eventually end up with an answer of 118.7 approximately units cubed. Okay, so the integration wasn't too stressful. Chucking in the limits was a piece of cake because it wasn't exact values. The hard part of this question was really rearranging the equation and then squaring it. So sometimes the setup is harder than the actual calculus. So that's why you got to practice all these questions to get comfortable with the setup, really, especially for y-axis questions. They're usually a little bit tougher. Okay, there's our first one. Let's do another one. This one is from the new Extension 1 course in 2021. It's 3 marks, and we're making another bowl sort of thingy. We're doing it, actually it's a really big bowl. It's a 2-meter high sculpture made out of concrete. We have the region between y equals x squared, which is the outer shell. And then we have x squared plus 1, which is the inner shell. And we're going from here up to 2, so y equals 2. I'm so sorry. Okay, and we're spinning around the y-axis to make this sort of giant cup thingy. And we're going to find the volume of concrete needed to make the sculpture. Okay, it hasn't said exact volume, but it hasn't asked for decimal places, so we're probably going to need to have an exact answer. Okay, so the tough part about this question is that it's kind of like 2 volumes questions in one, and also the picture they've given you is slightly confusing because there's no x and y axes. We can fix that by just chucking in our own axes and making it look like this. So now it's just a bit clearer that the outer shell is y equals x squared, and the inner shell is y equals x squared plus 1. And the lid is at y equals 2. Okay, so to find the shape, what we really need to do is find the volume of the whole thing by rotating the outer parabola around the y-axis. And then we'll find the volume of the inner part, which is the upper parabola, y equals x squared plus 1, rotating around the y-axis. And then we'll take away the little cup from the big cup to make the weird-looking, giant, freaky sculpture. Okay, so our approach here is big volume, take away little volume to give us this kind of like a shell, okay? So now we have a strategy, let's get into it. So we have our formula, which is rotating around the y-axis. We already have x squared for one of them. In the first one, the outer shell, x squared is equal to y, and we can very quickly rearrange the second equation to make x squared equal to y minus 1. So this time the rearrangement is very simple. It's just the concept and the setting up the equation. Figuring out how to do the minus is really like the challenging part. Okay, so here is what we're doing. We're doing the big outer shell, like I said, and then we're taking away the inner shell. So the outer shell is x squared equal to y, and the inner shell is x squared equal to y minus 1. For the outer shell, we're going from the bottom to the top, so we're going from 0 to 2. For the inner shell, we're just going from here, which is halfway, up to the top. So we're going from 1 to 2. Okay, so you've got to be a bit careful with your limits this time. Don't forget both have a pi at the front, of course. And now the integration is very straightforward. We're just going to y squared over 2 for the first expression. And we're going to y squared over 2 minus y for the second expression. Okay, now we'll sub in some values. We're going to have 2 squared over 2 here, take away nothing. And then for the second expression, we have 2 squared over 2, take away 2. And then we subtract from that 1 subbed in. So we get 1 squared over 2 minus 1 just here. Okay, thankfully these numbers are pretty friendly and it does simplify quite nicely, making a bit of space. So up here, we're going to get 4 over 2. So we're going to get 2. So the front term is looking like a 2 pi. For the second term, we have a 2 here, taking away a 2, and then we have minus a half, and then we have plus 1, because the negative makes a plus. Okay, so 2 minus 2 is nothing. Minus a half plus 1 is a half. So this whole bracket just turns into positive a half. So we end up with 2 pi, take away a half of pi. So 2 lots of something, take away half of something is going to end up with 1.5 of something. So we're going to end up with our answer being 3 pi over 2, or 1.5 pi, with our cubic units, of course, for our final answer. Okay, so nice and easy, straightforward calculus. The tricky part is just the question, the picture was a little bit tricky, and you just got to figure out how you're going to make this shape by doing big volume, take away little volume. But once you can sort of see that, the question is pretty nice in 2021. Okay, I think we're up to our last one, which is from the 2023 HSC. It's probably the hardest volumes question potentially that we've seen in the last few years. It was worth 4 marks. That straight away tells you there's a bit of work to be done here. We have a region R shown in this picture here. That's bounded by this hyperbola, little spoiler. We have this hyperbola 60 over x plus 5, which is this curve right here. But then we're cutting that curve off at the line x equals 10. Okay? So we're going up to the y-intercept, which we can see is 12. The curve is stopping at x equals 10. And then we have this shape here that we are rotating around the region, rotating around the y-axis to make a solid. Find the volume of the solid, leave your answer in exact form. Okay, so the trick with this question is this curve being cut off right here. Because we've stopped the hyperbola right there, we actually need to consider this, this question in 2 shapes. The first shape is this rectangle here. Now, when you rotate a rectangle around the y-axis, if you can picture that, it's going to turn it into a cylinder. Okay, this rectangle rotating around the y-axis is going to make a cylinder. Now, we don't need to use calculus to find the volume of a cylinder, because I'm pretty sure we all passed year 9, where we learned the volume of a cylinder is area of a circle times height, so pi r squared h. So we'll do that to find the bottom part, and then the top part we're going to need calculus, as you can see my incredible graphic design skills here. The blue part, wrapping around the y-axis, we are going to need to use calculus because the boundary is a function. Okay, so we've got 2 parts here. One of them's easy, one of them's a little bit trickier. Let's start off with the easy one, which is the volume of the cylinder. Pi r squared h, we can see the height is from here to here, which is 4. The radius is from the center of the rotation to the end point of the rotation, so the radius is 10. So we have pi times 10 squared times 4. Okay, 10 squared is 100, so we're going to end up with 400 pi for the volume of the cylinder formed by rotating this rectangle around the y-axis. Hopefully you can see that. If you can't visualize that, this question is probably confusing you a lot, and I'm really sorry. Okay, now for the blue part, we're going to take the function, which is y equals 60 over x plus 5. We've got to use our y-axis rotation formula, so we need to find out what x squared is. So we need to take this equation given to us by the question, we need to rearrange it to make x the subject, and then we need to square it. So there's a lot of work to be done here. Let's dive right into it. Starting off with our function, we are going to rearrange this by multiplying x plus 5 over to the left-hand side and then dividing y underneath the right-hand side. So these two guys are just going to swap places. X plus 5 is on the left now, and y is on the right, divided across. Okay, subtracting 5 from both sides, we now have x as the subject, and now we can do the tricky part, which is squaring both sides. So there's a lot of room for error here, so if you're going to stuff this up, you might want to do a couple of brackets and do a FOIL just to be safe. But if you're really confident with your perfect squares expansions, you can just dive into it like I'm going to do. So when we square 60 over y, we're going to get 3600 over y squared. When we times these two together, we're going to get 300 over y, which we're going to double to make 600 over y. And then for the last term, we're going to have minus 5 squared, which is 25. So we have the first term squared, we have the last term squared. The bit in the middle is these two times together and then doubled, and that's why there's a negative there. So this expression here in green is what we are now going to integrate. So we're going to think about how can I integrate this. These are two fractions that look deceptively similar, but they're going to be integrated in different ways. When we're integrating something over y squared, we're going to bring that y squared up the top by using negative powers. Now we can't do that with y to the 1 because then we'd have y to the negative 1 and then we'd end up dividing by 0 and it would break maths. So to integrate 600 over y, we need to use natural logarithms. So that's why I've written this as 3600 y to the minus 2, but I've kept this as a fraction because we're going to integrate the middle parts using a logarithm. Okay, I think this one can be simplified slightly because I'm seeing a lot of things that have a common factor of 25, so we can probably factor 25 out the front, make it a little bit more friendly. Okay, now we can do some calculus. And because our blue region is starting here at 4 and ending up here at 12, that's why my two limits are 4 and 12, if that wasn't already obvious. Of course, there's a pi at the front, otherwise the answer is incorrect. Okay, so integration, we are going to do some fancy transition, and then we're going to raise the power by 1 here to make this y to the power of negative 1. We're then going to divide by the new power of negative 1. Integrating 24 over y, we're just putting the 24 out the front and then using a natural log of y, because that's going to be 24 times 1 over y. And 1 just integrates to y. So here is our antiderivative calculated. Now we're just going to sub in 12 and sub in 4, and it's going to be a big mess. And from memory, this question said we want the exact volume, which is why this one is even harder, because we can't just chuck all this into the calculator and get a decimal. We need to have our answer simplified, which is going to take me a lot of lines of working and a lot of typing. So let's crack on, shall we? When we chuck in 12, we're going to have this y to the negative 1 going down below. So we're going to have a 12 on the bottom. We've got 24 log 12 here, and we've got 12 here. Now subtracting from that, subbing in 4, we're putting a 4 on the bottom here, putting a 4 in the log here, and then putting a 4 on the end here. Okay, now the goal is just simplify this as much as possible and then try and get 4 marks. Okay, so 144 over 12 is 12. There's a negative out the front. We've got 24 log 12 here, we've got a 12 here. 144 divided by 4 is of course 36, and then we've got 24 log 4 here, and then the minus out the front, making that 4 negative. Okay, combining some stuff together, we have a negative 12 and a 12 that cancel out. We have a 32 minus a 4 that makes 32. And now we have two logarithms that we're going to try and combine together. We have 24 log 4 minus 24 log 12. Gonna need a bit of room here. Okay, now to simplify the logarithms, what you need to keep in mind is that, what happened here? Yep, combining these two together, because we have two logarithms with the same number at the front and the same base, we can combine these together by using a division, okay? So log A minus log B is equal to log of A over B. And now we can actually be a bit clever with log 4 over 12. We can write that as log of 1 over 3 by simplifying the fraction. We can then write 1 over 3 as 3 to the power of negative 1, because when you have a log of something with a power, you can actually bring that power out the front, and so negative log 3 is the nice and simplified version of log 4 over 12. So we're going to sub that in here and make this minus 24 log 3. We've got the 32 here, we've got the 25 pi out the front, and now this is our exact expression for the volume of the blue region wrapped around the y-axis. We're also including the cylinder, which we previously calculated was 400 pi. So if we add them all together, we get our total volume of this part plus 400 pi, and that is an exact expression for the correct volume. So this expression, not a decimal, gets you full marks, 4 out of 4, on what I think was a high band 4 or maybe a low band 5 question in 2023. So pretty tough. Like I said, this is the toughest volumes question that we've seen in the last 4 years. So if that made sense to you, I think you're doing really well. And I think that's it for today. Example 6. Yeah, we're done. Okay, cool. Thank you so much for watching. If you made it through all of that, I hope that helped you if you were struggling with volumes of rotation. If you like these videos and you want to see some more revision topics, let me know what you want to see next in the comments below. If you're finding value from these videos and you want to support the channel, you can of course make sure you're subscribed, you can like, you can send this video to a friend, and yeah, I'll be doing a lot more revision videos in the lead up to HSC, so let me know what you want to see and I'll try and make it happen. I literally made this video because on my last video, 2 people said, make a volumes video, and I was like, yeah, why not? Okay, cool, that's enough rambling. Thanks for watching. I'll catch you guys in the next video. Bye for now, not forever.